Researchers at the Georgia Institute for Technology have found a new semiconductor that's a really good candidate for making computers faster and smaller than ever. Let's have a look. In 1965, Gordon Moore, one of the brains behind Intel, noticed that the number of transistors on a microchip was doubling roughly every 2 years. It's become known as Moore's Law, and it has roughly remained valid until a year ago or so, when NVIDIA declared Moore's Law dead. The problem is that by now, the size of transistors that are the elementary logic components of computers are mere nanometers in size, and it's becoming increasingly difficult to squeeze more of them into smaller space. You see, the issue is that transistors are getting close to the size of single atoms. At that point, quantum physics becomes important, and that makes things much more complicated. It doesn't make it impossible to shrink things down further, but you'd need to come up with something entirely new. Sure enough, researchers are working on entirely new stuff such as spintronics or quantum dots, etc. But these are still quite far in the future, and from a manufacturing perspective, they're somewhat unappealing because they'd require many changes. The path that most chip makers are pursuing for the moment is to stack transistors on top of each other. At present, transistors are etched into flat silicon surfaces next to each other, but if you could stack them, then you could get more computing power into small spaces, and that'd continue Moore's law, if by other means than previously. If you stack transistors, however, you get a new problem, which is that they just get too hot. One way you can try to address this issue is with some sort of cooling technology, like tiny channels with liquids or such. But again, the issue is that from a manufacturing perspective, this is unappealing because you can't continue producing your microchips as previously. The most convenient thing you could do to continue Moore's law is to find a material for transistors that's better at giving off heat than silicon, but that can largely be used with the existing production technologies. And we know such a material. It's graphene. You've probably seen images of graphene. It's a single layer of carbon atoms set up in a honeycomb pattern. The great thing about graphene is that it gives off heat enormously well. So it's rather unsurprising that the idea of graphene transistors has been around ever since the material was discovered in 2004. But while graphene is good at giving up heat and is very good at conducting electricity, it's unfortunately not a semiconductor. You see, a semiconductor is a material to which you can apply a current to make it switch from a non-conducting to a conducting state. For this, you need what's called a band gap in the electron bands. If you apply a sufficiently high current, that'll propel electrons to the upper band, and the semiconductor will conduct. That's why you can use them as logical elements, because you can switch them on and off. But graphene doesn't have a good band gap. Graphene is considered a quasi-metal because while it strictly speaking isn't a metal, it conducts electricity much like one. And this means it can't fulfill the function of a transistor to act as a switch, at least not the way it is. Scientists have come up with several ways to try and fix that. For example, they've used graphene rolled up to tubes called carbon nanotubes. These can be switched between conducting and non-conducting by twisting them, and that can be used to make transistors from them. But the issue is again that producing these nanotubes and using them to build microchips is too cumbersome for mass production. The authors of the new paper now did something completely different. They grew a layer of graphene on wafers of silicon carbide. Silicon carbide itself is a semiconductor, and it's one with a pretty big band gap. Basically, they figured out that they can combine the silicon carbide with the graphene to get a stable material that both has a band gap and still gives off heat 10 times better than silicon. They have also very thoroughly documented exactly how they produce the material and have tested that it's strong and stable enough to be used for transistors. This is pretty exciting, honestly. After 20 years of graphene talk that didn't amount to much, it could finally go somewhere. But it's a long way from the laboratory to the shopping mall, and many nice ideas have died on that path. So I'm afraid we'll have to wait a little longer until we can breathe transistors together with the microplastics. We've heard that space debris is bad and the problem's getting worse, but here's a new thing to worry about. It could interfere with the Earth's magnetic field, which is our major protection from the highly energetic particles of the solar wind. Space debris, aka space junk or orbital debris, comes from stuff like defunct or decommissioned satellites or spent rocket stages. It already poses a significant challenge to the sustainability of space activities, and as more junk accumulates up there, the risk of collision increases, which will spread the debris further and make it harder to track. The potential for cascading collisions of space junk is known as the Kessler syndrome, named after Donald Kessler, a now retired NASA scientist. Kessler pointed out already in 1978 that if we put too much junk into orbit, that'll eventually reach a critical density. Then one collision will cause a chain reaction of other collisions, and this could eventually splatter debris all over the most precious orbits, making them unusable for potentially millions of years. The problem's becoming more and more pressing now because a lot of companies, including Elon Musk's SpaceX, are shooting huge amounts of satellites into Earth orbit. By some estimates, we might reach 100,000 by the end of the decade and up to 1 million in the decades afterwards. Efforts to mitigate space debris so far involve a lot of guidelines about how to responsibly decommission satellites by burning them up upon re-entry in the atmosphere. Indeed, the European Space Agency recently tested this with the Aeolus satellite. After nearly 5 years of collecting wind data, they guided the satellite back through the atmosphere over the Antarctic, where it burned up as planned, and not even the penguins raised any eyebrows. Do penguins have eyebrows? The author of the new paper now points out that, well, burning the stuff doesn't mean it disappears. It's just that now you've distributed a lot of soot and ashes and very finely powdered debris in the upper atmosphere. Some of this stuff rains down on Earth, some of it lingers around in the stratosphere, and some distributes in layers further up. Indeed, according to a recent study, about 10% of the small particles in the stratosphere now contain metals that almost certainly come from space debris. These particles are called re-entry aerosols. Of course, it's not just satellites and rockets that burn up in the atmosphere, there are also meteors, but their chemical composition is different. Man-made stuff tends to contain more lithium, lead, aluminium, and copper. As you might have noticed, that's a lot of metals, and while data is hard to come by, this stuff will also accumulate in the atmosphere above the stratosphere, especially in regions called the plasmasphere, magnetosphere, and the Van Allen belts. These are different regions, but they have in common that they trap particles. Those particles then lose electrons from solar radiation, so they become charged, and that makes them interact with the magnetic field. The author of the new paper now says that since a lot of the space debris is metals, these new bands will by all chance conduct electricity, which in return will generate its own magnetic field. You might say, well, but there's already stuff up there, so it doesn't really matter if we add something to it. But the amount of mass that we put into orbit is dramatically higher than that which gets there by natural causes. According to the paper, since the beginning of the space industry, approximately 20,000 tons of material have been demolished during re-entry, most of which stayed up there. This mass is over 100 billion times greater than the total mass that's estimated to be in the Van Allen belts. It'd be bad if the magnetic field that surrounds Earth were to weaken because it's our major protection from solar wind. Solar wind is made of highly energetic charged particles, and these get mostly deflected by the magnetic field. Not only is it unhealthy if we get hit by highly energetic particles, but without the magnetic field, Earth would probably also lose its atmosphere. Indeed, this is what scientists think happened to Mars, that it once had an atmosphere, but since it has no magnetic field, that atmosphere was basically ripped away by solar wind. And as if unhealthy radiation and being unable to breathe wasn't quite bad enough, all that solar wind would also ruin your phone. Now, I don't want to be alarming. The paper doesn't say exactly what's going to happen because, quote, after consulting multiple magnetosphere models, the consensus was that it'd take decades to simulate 500,000 satellites. But the magnetic field of Earth is not created by the atmosphere, but rather by its core, where liquid metal is sloshing around. So it's not like Elon Musk is going to kill us all with satellite debris. At least, I don't think so. Still, it's another example where I feel like, guys, maybe we should think about the consequences before doing it. It's hard to keep track of all the things that'll supposedly fix climate change but won't, such as hydrogen, veganism, or quantum computing. Wait, what? Yes, marketing quantum computers as a miracle cure for climate change has not fallen out of fashion despite my many jokes about it. For example, in a recent article in The Hill, Sam Howell, a research associate at the Center for New American Security in Washington, D.C., writes, "If countries are serious about climate change, they should get serious about quantum computing." Right, if we put all our money into quantum computing, there'll be none left for oil. Problem solved. But quantum computing hype isn't new, and this is supposed to be science news, so let me tell you what's new. New is that Jan LeCun, the AI chief of Meta, has a surprisingly sane attitude to quantum computing. This deserves celebration and also investigation, because he's making a very good point. According to a recent report by CNBC, he said that the practical relevance of quantum computers is unclear, and that many of the problems you can solve with quantum computing, you can solve way more efficiently with classical computers, and that quantum computing has got such a long time horizon that it's irrelevant to what they're doing at Meta. I found this to be very interesting because it draws attention to the competition between artificial intelligence and quantum computing that's becoming increasingly noticeable, and that might just be the final nail in the coffin that is commercial interest in quantum computing. I thought it'd be worth looking at this a bit closer and explaining what I believe he meant. You see, quantum computing is extremely exciting from the research perspective because it's completely uncharted territory. We've never used such big quantum things before. But getting commercially relevant results out of quantum computers is another thing entirely. Not only do you need the computers to be big enough and still stable enough to maintain the fragile quantum states, you then also need to demonstrate that they can do something better than a conventional computer. And this requires two things. First, you'll need an algorithm that can run on the quantum computer that has a computational advantage over a conventional computer for some sort of interesting problem. And second, you'll have to show that in reality it'll actually come out faster. The best understood quantum algorithms are those for certain problems in quantum chemistry, that's basically material science, some problems in logistics and finance, and some sorts of code cracking. It's a rather limited class of problems. Of course, the companies who want answers to these problems already have pretty good algorithms on conventional computers, and these are now further improving with artificial intelligence, which is why the current AI boom is bad news for quantum computing. But how is this even relevant if quantum computers are supposedly unbeatably fast? It's because of what gives them their advantage. Quantum computers work with quantum bits, qubits for short, and derive their advantage from the many ways you can correlate or entangle those qubits. But it's not that operating the qubits themselves is fast. Indeed, operating qubits is usually slower than doing operations on a conventional computer. Keep in mind that modern computers operate in the gigahertz range or above. That's more than 1 billion operations a second. How fast you can operate qubits depends on the type of qubits, but for superconducting circuits, it's maybe 10 million per second optimistically, and ion traps are much slower still. And that doesn't take into account the need for error correction, which will make them even slower. The reason people are excited about quantum computers is not because they're fast per operation, but because they need fewer operations to get the same result. So you see, if you have a small calculation on a conventional computer, one that requires fewer operations, it'll beat the quantum computer because the conventional computer is faster per operation. If you increase the size of the problem, then both the conventional computer and the quantum computer will need more operations and so more time. But for the quantum algorithm, the number of operations increases less with the size of the problem. So the idea is that regardless of how slow the qubits are, eventually the quantum computer will outperform the conventional computer because it needs fewer operations. That's the theory. In practice, the question is where this crossover happens, where the quantum computer starts to outperform the conventional one. That's a moving target, because each time conventional computers become faster or someone comes up with a better algorithm, the point where quantum computers finally win moves further away to a higher number of qubits. And this is why artificial intelligence is becoming a problem for quantum computing, because artificial intelligence lets you get more out of conventional computers, and the number of qubits at which quantum computers will bring an advantage might eventually become so large that it becomes impractical or just prohibitively expensive to even use them. Though it's a shame that Meta isn't more into quantum computing. I'd really like to have a button that's thumbs up and down at the same time. When I was just about to log off for the holiday break, I saw these headlines popping up saying that it doesn't take much to turn Earth into Venus with a runaway greenhouse effect, which would, quote, literally burn Earth alive. I thought it'd be best to ignore this. But then I saw that some people on social media got first worried about it and then confused because no one was addressing this. So I decided to, give you all the boring context, because that's what I do. And here we go. A runaway greenhouse effect happens when a planet loses its ability to cool. Then the only way for the surface temperature is up. This might happen, for example, when the amount of water vapor in the atmosphere increases beyond a critical threshold. That's because water vapor is an incredibly potent greenhouse gas. And also, the warmer the planet, the more of its water will be in the form of vapor. So, higher temperatures lead to more water vapor, which leads to higher temperatures, and the effect can, run away, hence the name. Scientists believe that a runaway greenhouse effect is what happened to our neighbor planet Venus. Venus is in size and mass not too different from Earth. When it was young, it was probably quite similar to our planet, with liquid water on the surface. But Venus is somewhat closer to the Sun than we are, and since it received more sunlight, the amount of water vapor in its atmosphere was higher. At the same time, the sunlight was powerful enough to split the water vapor into oxygen and hydrogen. And here's the problem: the hydrogen escaped into space. This is bad because with the hydrogen gone for good, the water cycle couldn't stabilize. And water is good to absorb carbon dioxide from the atmosphere. So as the hydrogen fraction decreased, the carbon dioxide in the atmosphere steadily built up, covering Venus in a thick blanket that retained heat very well. Today, the atmosphere of Venus is mostly carbon dioxide. The water is all gone, the atmospheric pressure is about 90 times that of Earth, and the surface temperature is roughly 370 degrees Celsius. If you've sometimes dreamed of plucking chickens out of the air fully roasted, then moving to Venus might be the right thing for you, though you'd have to take your chickens with a side of sulfur. The rest of us, I guess, would find Venus a rather unpleasant place to live. Now comes this press release from researchers at the University of Geneva, which says, quote, with their new climate models, the scientists have calculated that a very small increase of the solar radiation, leading to an increase of the global Earth temperature of only a few tenths of degrees, would be enough to trigger this irreversible runaway process on Earth and make our planet as inhospitable to life as Venus. Given that human-caused global warming has already increased the global temperature by much more than a few tenths of degrees, this sounds hugely alarming. Indeed, an article that was covering this press release warned that we could cause such a runaway greenhouse effect by increasing carbon dioxide levels. It's a grim warning of just how stark a future of human-driven climate change can look. So, watch out. Here comes the context. First, let's have a look at solar irradiation. That's the radiation from the sun that reaches the surface of Earth. It's basically a measure for the energy we get from the sun. It fluctuates naturally and goes somewhat up and down during the solar cycle. These fluctuations do have an influence on the temperature on Earth of typically a few tenths of a degree. That's noticeable and accounted for in the IPCC projections, but it's smaller than the effect from human-caused increase of carbon dioxide levels. Though the brightness of our sun very slowly increases as it gets older, and that'll eventually cause a runaway greenhouse effect on Earth too. According to estimates, we've got 1 or 2 billion years. So Elon's got some time left to get us off this planet. For all I know, if you wanted to substantially increase solar irradiation any sooner than that, to levels so high that it'd trigger a runaway greenhouse effect, you'd have to move Earth closer to the sun. So if these scientists say that small changes in solar irradiation can cause a runaway greenhouse effect on Earth, I'd really like to know what small means. Numbers, people, show me numbers. I looked for the numbers in the paper, and would you know it, the paper doesn't so much as contain the word solar irradiation. What they did in the paper is that they increased a model parameter called the insolation of a planet. Increasing this insolation prevents the simulated planet from cooling, and then they keep track of what happens. The reason they did this is that they want to better understand under which circumstances life might be possible on exoplanets. The paper doesn't say anything about a runaway greenhouse effect on Earth. The press release just quotes one of the authors as saying that they'd like to study this in the future. What do we know about the risk of a runaway greenhouse effect on Earth? Well, we do know that the past of our planet has had phases that were both hotter and had much higher atmospheric carbon dioxide levels than we have today. Not only this, but it was sometimes also higher than what we're likely to reach even if we keep on happily burning fossil fuels. This shouldn't be all that surprising because the carbon in those fossil fuels mostly came from the atmosphere in the first place. And since no runaway greenhouse effect happened back then, it seems unlikely we'll trigger one now. It also hasn't happened in any climate models, most of which are much more sophisticated than the one the guys in the new paper used. The problem with climate change is really not the temperature or the carbon dioxide level per se, it's the rapid change. We and the rest of the biosphere must adapt to the changing climate within a matter of decades. That puts a lot of stress on our economies and brings the risk of a strong economic downturn. It's bad enough as it is without having to make people afraid of a runaway greenhouse effect. Of course, I can't say that the risk is indeed zero, because God knows what other stupid ideas humans will come up with to meddle with the climate. But really, I think a runaway greenhouse effect is not something we need to worry about. No matter how much they dig up in Saudi Arabia, it's not going to move the Earth closer to the sun, I promise. A lab in Australia is building a new supercomputer that'll for the first time both physically resemble a human brain and perform as many operations, about 228 trillion per second. The scary bit is how few operations these are. Yes, how few. Let me explain. The new supercomputer will be built at Western Sydney University. It's part of a new paradigm called neuromorphic computing. That's computers modeled after the so far best processing apparatuses that nature has given us. Brains. Neuromorphic computing isn't the same as artificial intelligence. These are two different research areas with different goals. What they have in common are neural networks. You may know neural networks as the most important software behind artificial intelligence. But while these neural networks do in some sense resemble the neural networks in the human brain, they're different from the real thing in one very important way. It's that for AIs, the structure of the neural network is represented in the software, but the physical basis is still transistors lined up on microchips. In the human brain, in contrast, the network is a physical thing. It's one with the algorithm that runs on it. This difference is what scientists and engineers want to remove with the neuromorphic computers. These are built to resemble a human brain in terms of hardware, not just in terms of the algorithm that runs on it. This doesn't mean that they're built from biological tissue, it just means that the connectivity and functionality of the biological tissue is reflected in the structure of the neuromorphic processor. So the thing doesn't actually look like a brain, it's still a box with wires in it, but it works differently than your phone. The term neuromorphic is somewhat vague and encompasses a lot of different things. In some research settings, for example, they basically throw a bunch of wires atop each other to create a network and call that neuromorphic. Some researchers have succeeded with teaching these wires to recognize hand-drawn numbers by adjusting how well the junctions conduct electricity, and from there it's just a small step until they run for president. Somewhat more sophisticated than a handful of wires is IBM's True North processor that they first put forward in 2014. It had 1 million cores, each designed to resemble the way neurons fire in the brain, and specifically designed to map the virtual neurons of a neural net onto the physical ones. IBM has since updated and improved its neuromorphic processors, but they're still far smaller than the human brain. The new computer to be built in Sydney is named Deep South, not just to acknowledge its location, but it's also a nod to Google's DeepMind and IBM's True North. The new computer will, however, work completely differently than either. The researchers in Sydney want to use what's called field programmable gate arrays that are basically small circuits whose function, in contrast to normal microprocessors, can still be electronically changed. These programmable arrays will take on the function of neurons and simulate in particular the spiking. That's the rather sudden threshold at which neurons pass on information. In addition, they'll be building in some randomness into the behavior of these artificial neurons, because that seems to be playing an important, if not well understood role in the human brain. The point of this research project is not to build a super powerful computer. That'd be more difficult because then you'd have to figure out how to train this neural network. For the moment, they just want to find out how the human brain manages to run on so little power. It barely needs 20 watts to operate, whereas training the currently existing artificial intelligences consumes huge amounts of energy, and running them isn't cheap either. Sooner or later, this will become a problem. Mapping the neural networks from the software to the hardware could dramatically decrease the energy requirement. Another reason that they use these field programmable gate arrays is that they are slow. You see, neurons in the human brain need a few milliseconds or so to update their state because it's all chemical reactions. You might find that fast, but remember that modern computer processors update billions of times a second, so they're easily 1 million times faster than the neurons in our brains. If you want to build something that physically resembles a human brain, therefore, you need slow electronics. So this is what they'll be doing. The researchers plan to complete the Deep South computer by April this year. It'll be remotely accessible for research purposes, though I suppose the waiting list will be quite long. Of course, this opens the possibility that once they've managed to get this done, they might be able to build a device that works like a human brain but 1 million times faster, which isn't scary at all. Hello. Hi, Elon. I've been telling you all good things are called something with deep. Deep space, deep mind, deep fry. Deep X? I don't know, it sounds like a medical condition to me. You're welcome, bye. I hope you're enjoying our science news. I know it can be hard to keep track of what's going on in science, but I also know a solution. Nautilus is a science magazine that keeps you up to date on the most relevant topics that are being discussed today. They frequently have scientists writing for them who will tell you the inside stories. What I particularly like about Nautilus is that they cover all areas of science, from astronomy to economics, history, neuroscience to philosophy and physics. Nautilus comes with a digital and the print version, and it's just a pleasure to read. They really put a lot of effort into writing, and the graphic design is top. If you use our custom link joinnautilus.com/Sabine, you'll get 15% off your membership subscription, so go and check this out. Thanks for watching. See you tomorrow.